Hello students, and today's class we are going to see about the monochromators, right, which is present in the spectrophotometer, which is most important component to get the exact wavelength. And these monochromators are better than the filters. So in the last class we already seen about absorption filters. Now we are moving to monochromators, which are more popular and more accurate than the filters, right? And so monochromator is a device that uses two slits. One is for entrance and another is for exit. Slits are nothing but a hole like structure from the light can pass through and the light getting out. Okay, so spectral scanning can be achieved by transmitting different wavelength bands one at the time through the exit slit. From the entrance slit we can pass through the polychromatic radiation from the light source. We can get the exact wavelength at the entrance exit slit, right? If you see, you can, if you see the picture you can understood, I think, right? And here this white color is entrance slit which has the polychromatic light. When it goes and hit the mirror, one reflective mirror, and again it hits the instrument or component of main component, core component of the monochromator, maybe a prism or maybe a grating. Here it is grating monochromator, so the slide is placed there. You can see that in Vibgyor colors in that the spectral formed and which is reflected again to the mirror, to the reflective mirror. By this mirror, from this mirror we can get the colors by putting the exit light and the correct position. In this example, the only green waves are getting out, right? If you move this light into the top, we can get the pink color. If you move the bottom towards the bottom, you can get the orange color. Okay, and this monochromators for UV visible and IR radiations are similar in mechanical construction, which means it has more or less similar components. It contains slits. One is entrance slit and another is exit slit, and the lenses for collimating, and the mirrors for reflecting, and windows, which is nothing but a cabinet, and grating or prisms to produce the monochromation light. Okay, then the components of monochromators, the first one is entrance slit, where the light can enter into that. The collimating lens or mirror, which can produce the parallel radiation beam of radiation, and the prism or a grating to disperse the radiation. We have the use of the prism or the grating is to disperse the radiation and to get the spectrum. A focusing element that reforms the image of the entrance slit and focuses it on the planar surface is called focal plane, right, where we can get the exact bandwidth. Okay, then an exit slit in the focal plane that isolate the desired spectral band. We already knew that if we move that focal plane, we can get the bandwidth what we are needed. And in addition, most monochromators have entrance and exit windows designed to protect the components from dust and corrosive laboratory fumes, right? Spectrophotometer, this is the inner component. It is highly closed and protected, right, because dust can interfere and produce the noise in the signal, right? So we cannot get a accurate result. Okay, reflection gratings and prisms are the type of the monochromators. These are mostly used in dispersing elements. These two things, grating and prisms, are used for dispersion. Okay, in reflection gratings, radiation enter to the monochromator via narrow rectangular opening slit, which is the way right? Then collimated by the lenses or the mirror and strikes the dispersion elements at the angle, right, where the reflection gratings are present. Angular dispersion of the wavelength results from diffraction which occurs at the reflective surfaces. In this picture you can see that my god, what happens, we can go through this, and this is the entrance slit. You can see that there are polychromatic light. For example, they are using lambda 1 and lambda 2 here, and the light rays get hit at the mirror, reflective mirror 1, and get reflected to the place where the grating is placed. Okay, that is reflection gratings. From that reflection gratings there is another a reflection takes place due to the gratings, so we can get the light rays at the exact position at the particular angle. So concave mirrors are the next concave mirror, that is M2 or reflecting mirror you can use, collimating mirror, whatever the phrase you can use for that, reflecting the light rays. So by this way we can get the two types of wavelengths, right? Lambda 1 and lambda 2. In actually we can get the entire wavelength. If you move here, they're giving only lambda 1 lambda 2. If you want to get, you can get lambda 10 lambda, anyway anything you can get in this band. Okay, so depending on the focal plane only it can get, we can get from the slit. This is the picture you should draw and you should get in your answer script, right, as a block diagram. Kindly note this and practice this, how to draw and all those things. Then next one is prism, a refraction at the two faces resulting in angular dispersion of the radiation, right? I see this is the prism. In that you can see that mostly avoid that lambda 1 and lambda 2. You just draw that, this just put it that this is a polychromatic light from the entrance slit. As goes in, collimating lenses are there to give the parallel beam of light. After that it hit the prism. During that prism you just look at that there is a refraction is happens, right? And one is gray in color and one more is blue in color. So the blue color gets the angle and the gray color gets another angle. So we can get the likewise here as per the example they have given the two lambdas, lambda 1 lambda 2. You can get more, right? You can get a series 1 up to the entire slit. So by moving the slit you can get the wanted wavelength. Prism monochromators, UV visible and IR radiation. Carnot prism and litho prism are the two types. The basic principle is it should get 60-degree prism, right? A prism 60-degree fabricated from a single block of quartz, nothing but a glass, type of glass with a piezoelectric effect. Okay, formed by cementing two 30-degree prisms together, also possible, right? Actually this has happened. If we want to get a 60-degree we can get it a single one, or we can make it by 30-degree to get that. Okay, one is fabricated from right-handed quartz and another is from left-handed quartz for the refraction condition. Okay, coming to the litho prism, more component or more compact monochromator designs, because it is very small. A 30-degree prisms with a mirrored block is constructed. Then refraction takes place twice at the same interference, so that the performance characteristics are similar to those of 60-degree prisms. And the basic principle is the light get 60-degree reflections. So here they are making two 30-degree reflection, so we can get the wanted lambda. This is the example. You can see that. Where is Carnot prism and litho prism? See, Carnot prisms with a triangular prism which has the white light rays hit the one side of the prism and another side it gets separated at the VBR, right? This is Carnot. This is 30 plus 30 degree reflection is taken place, refraction is taken place. And here coming to the litro prism, you can see that the simplest one, the first same white light is hitting the surface of the prism, and what happens at the 30 degree, it again get reflected, right? And this is actually made by 30-degree prism with one side highly reflective material. Okay, so we can get the same one VBR like the Carnot prisms. So we can use this very simplest one and very space accommodated one. Okay, the same principle is given in your book. Dispersion by a prism happens, and you can see the block color lines, which how it gets transmitted and separated as a colors, right? The same thing in the B, you can see that this is a mirror, a highly reflective mirror. The incident light goes and hit and come back, so two times it gets reflected, one times it get reflected, and two times it travels through the quartz. So the same results we can get it from the litroprism. Okay, grating monochromators. So grating means nothing but a line which has the grooves. From the groove, the light gets reflected and refracted. So by this way we can get the exact wavelengths. Here there is a chance to get more number of, which means the n number of wavelengths, right? The ranges will be reduced, so we can get the narrow down wavelengths. That is the advantage of this. Dispersion of UV visible and IR radiation can be obtained through transmission grating or reflecting gratings. Two types of gratings are used, and replica gratings or master gratings, we can say that this is master grating because it was done by machines, right? Replica gratings means the lines are same length and same distance, okay, but is uniform, that's why it is called as replica gratings consist of a hard, optically flat, polished surface that has a large number of parallel and closely spaced grooves, right? That's why I told you that is uniformed grooves made with a diamond tool. So we are going to make in a groove on a glass, right? So diamond are used to scratch that or make a groove on that. Okay, construction of a good master grating is tedious, time consuming, expensive, because grooves must be in ideal size, then only we can get the expected wavelength in the particular distance. So exactly parallel and equally spaced over the length of the gratings, nearly 3 to 10 centimeters is the total length of the grating space, and in between that you can get nearly 2000 grooves, right? Okay, the surface is usually made reflecting surface by a coating of aluminum or sometimes gold or platinum. Usually we are using aluminum, strictly speaking. There is gold also we can use, but gold plated are used now, right? The platinum are I didn't hear that platinum may be that properties, but they are not using commercially. Platinum grating monochromators are not used. I didn't come across. Okay, UV and visible regions, moreover you can get 300 to 2000 grooves per millimeter. See that per millimeter you can get 2000 and lines, and by manual it is not possible, right? So that's why it is called as replica grating or master grating. Okay, 1200 to 1400 being the most common one used in UV and visible regions. For IR regions, 10 to 200 grooves per mm, right? 200 grooves per mm, because that wavelength is lengthier than the UV and visible, so that this much is enough, I think. So 5 to 15 micrometer, a grating with 100 grooves with is more suitable and more common in the IR FTIR analysis. Okay, H-lit grating. This is the example of that grating monochromata. Uh, Sometimes questions may arise like describe the principle of monochromatas. For those conditions, you should select this H-lit grating to explain the principle, how it get reflected and how can we get the wavelengths, different wavelengths. Okay, it's a grooved or blazed and concentrate the radiation in the preferred directions, which means the surface where I expected to be hit by the light waves, right? You can see that. So okay, I will show you when I am enlarge the picture. And next is broad faces from which reflection occurs. Narrow unused faces provides highly efficient diffraction or radiation, right? That is narrow, that is the advantage of this H-lit grating. Each broad faces can be considered as a line source of radiation. We already knew that, line source, continuous source, like that, and each and every broad spaces as considered as a line sources here, which allows interference among the reflection beam, which are all coming towards the surface of that grooves. For constructive interference, it is necessary that the path length differ by the integral multiple number of wavelengths lambda of the incident beam. We have to define that, and which is possible to us. See that, and this is the diffraction mechanism of the wavelength selector, how it shows. And D, in this we already knew that D is the path length of light waves, which is by dielectric component in interference filters, right there. Here in the refraction filters, there is a glass plate actually grooved by diamond tool. The surface, the upper surface is a rough one, which is the grooves, and we can easily say that the light can hit at the A or the B. It cannot hit at the lower bottom of the curve, right? So we can easily predict that angle, in which angle it can be reflected. So by this way we can find where the our own interested wavelength is coming. Okay, in the see 1, 2 and 3, waves are hitting the surface of that gratings, and it gets reflected at different angle. So different beam you can get the uh, different wavelengths by calculating this angle. Okay, other wavelength selectors, polychromators and spectrographs. Monochromator isolates one wavelength band, right? Because it is more efficient. A polychromator isolates several wavelength bands. It has several exit slits. That is the main difference in monochromator. It has now one entrance slit and one exit slit. When come to the polychromators, they have the many entrance slits, sorry, exit slits. Okay, we can get at a sign time at any wavelengths. A radiation transducer is placed behind each exit slit, allowing multiple wavelengths to the monitor to be monitored. Okay, useful in atomic spectroscopy, allowing lines from several different elements to be monitored simultaneously. Then spectrographs actually has no slits, only an entrance slit. Exit, there is no exit slit, it has only the entrance slits. Spectrum is displayed spatially in the focal plane. See that in monochromator it has one entrance and one exit slit. In polychromators it has a one entrance slits, many numerous exit slits. We can place a sample anywhere what we want, where we want at the particular wavelength. And in spectrographs there has no exit slit at all, right? There is only entrance slits. Then this spectrum is displayed spatially in the focal plane. The colors can be easily differentiated in the focal plane. Multi-channel transducers consisting a array of small photosensitive elements are used. So photosensitive elements are used to get the array of that wavelength, and the multi-channel transistor is placed in the focal plane of the spectrograph. If you want, you can see this, how there is a only entrance slit is there and get reflected. Grating is happens. After gratings again hit at the mirror M2. From that you can see that photo sensitive material, right? We can get the wavelength. There is no exit slit in that. Acoustic optic tunable filters. It disperses incident radiation based on the interaction with the ultrasonic wave in the acoustic optical crystal. That's why it is called as this. Here it is used. We already seen about the prism monochromators, right? By using the triangular glasses, and here they are using a crystal. Those are acoustic optic crystals, right? Which means it has a piezoelectric transducer bonded to by refringed crystals, which means a line sourced crystals. When a radio frequency signal is applied to the transducer, an acoustic wave is generated. See that here we are using radio frequency, so it is mostly used for IR. Okay, so FTIR analysis. The important thing is it is ultrasonic waves in an acoustic crystals is used, and the acoustic wave propagates into the birefringed crystal. The wave propagates and hits where it causes periodic changes in the refractive index. Okay, and the crystal act as transmission diffracting gratings, disperse the incident radiation according to its wavelengths. When the radio frequency is varied, we can vary it, right, to get different wavelengths. So the period of the refractive index variation changes and a different band of wavelength is transmitted, and this is the main principle of that. When we give the different wavelengths, when we give the different radiation, incident radiations frequency, we can get the different wavelength or frequent or altered frequency. Okay, tuning occurs very rapidly. The tuning is nothing but getting the varies lambdas, varies wavelength, which happens only microseconds by changing the RF frequency. When we change the radio frequency waves, we can get the different wavelengths. Okay, applications: fluorescent microscopy, and mostly it is used in near IR. Okay, this is about our filters and monochromators. In the next class we will see about the radiation transducers. Thank you guys. Before going to the class, I am just showing you where I am sitting to take a class for you, and this is Kaveri water. This channel is from divided from the Kaveri river, actually Kollidam river. See there, and moreover this is the place where I was learnt swimming at my 10th age. I think age of 10 15 10 to 15 I was here, and those days these are very big canal for us to play. And this is the Attiparam. This is the thing we can get it at nearly 70 rupees in shops. Okay, and these are Udayamaram, you knew, I think, and others are Teku and Panai.